so the second section in chapter 6 has to do with the conservation of momentum. So we talked about our definition of momentum from section 6.1. Remember, P equals mv, and that was from section 6.1. Section 6.2 is going to talk about objects that have conserved momentum, similar to conservation of energy. So if you remember from energy methods, we said the mechanical energy before equals the mechanical energy at the end. And that was our energy balance. That gave us our equation. It's going to be the same thing here. The total momentum of a given system before an interaction is equal to the total momentum of the system after some interaction. Now, what do I mean by that? Here's what I mean. If you took two objects, okay, let's take a look at these toothpicks, and these are popsicle sticks, and you slid these toward each other, okay? They're going to rebound, or they're going to, in this case, they have to stick together. You see how they end up moving? They rebound a little bit this way because there was more momentum from this one because it's bigger. That's what we're doing today. What we're doing really is thinking about when two objects collide, what's the result of it going to be? So we're really trying to look at problems where there are collisions, or we could say interactions. So for this first part here, okay, let's take a look at our equation for this. So if you remember energy, so if you want to just think about it, you don't have to write this down. But for energy, you remember this. Okay, and we said all the energy beforehand is equal to all the energy at the end because the total energy is conserved, or it's the same throughout the whole process. Today, in section 6.2, we're going to talk about momentum being the same. So we could say that the sum of the momentums beforehand equals the sum of the momentums afterward. It's the same equation, really. It's the same idea, but the first one had to do with energy, and the second one at the bottom here that we're looking at today has to do with momentum.
Wait, this doesn't have to do with anything with PM or V.
It's going to be PM, yeah. Not impulse theory, though, no. Impulse theory was 6.1. It's going to be conservation.
Equals FT,
Okay.
it's not that.
It's not going to be the FT problem. No. So what we're saying is this. Think about it specifically for the scenario I just gave you. You've got this one object with the popsicle sticks that has a high mass, this other object with toothpicks that has a low mass, okay? And think about the fact that they can collide. And beforehand, if I took both of these and slid them toward each other, they both got mass and they both got velocity. They collide, and they actually did this before. So so there's this initial velocity and mass, they collide, and there's some final velocity and mass. And what we're trying to do is think about what is the result of a collision, what happens afterward. Okay, so that's what we're going to think about. So we have to say for ourselves, how many momentums are there initially, how many momentums are there at the end? And it depends on the problem itself.
If you threw the smaller object with less mass, like with a greater velocity, would it cause the other one to move?
Sure, just like the running back and the linebacker. Remember, if two people are running at each other, and one is much heavier than the other, if they're going at the same speed, the heavier one's going to win the battle.
That just break on contact.
Well, that's different. You're talking about the tensile strength of the plastic. And that's has nothing to do with the actual object. I mean, it does in a sense, but for the sake of collisions and momentum, you think about a transfer. It's not like this object will break or anything like that. Okay? So what we can say is this. For a two-body system, which is what we're going to really look at, meaning two objects colliding, we can do this where there's 3, 4, 5 objects colliding at once, but the equations get much more elaborate. For a two-body system, we have the momentum of object 1 plus the momentum of object 2 initially equals the momentum of object 1 at the end plus the momentum of object 2 at the end. Okay, remember I said there's a lot of subscripts in this section? This is what I wasn't joking about here. P1I means the momentum. You should write this down in words because I don't know how many of you keep forgetting what variables mean. On the test I kept noticing it. People were trying to list variables that didn't make any sense at all. Okay, you got to know what stuff means. This here, P1I, means the momentum of object 1 initially. P2I is the momentum of object 2 initially.
If it helps us, can we spell out 1?
Sure, it helps you absolutely. Yeah. So you don't see the, because the I and
No.
one look similar, that's fine. This part, P1F, P2I is the momentum of object 2 initially. Just read it as you see it. Okay, so this is what I see. I see P1F over here. I see this means momentum of object 1 finally, or at the end. Over here, the momentum of object 2 at the final stage or at the end. Okay? So simply go through your variable and look at your subscripts and it will tell you what it actually means. Now, remember though, there's another side note, remember P equals mv really. Momentum is mass times velocity. Momentum is mass times velocity. So what I can do with this equation, is replace the P with mv. Before I do that, don't write anything down, just watch please. All of these become mv. The question is, what are their subscripts? So this is the momentum of object 1 initially. So we have the mass of object 1 times the velocity of object 1 initially. Okay, the board is off, which is killing me right now because the subscripts look like they're off. They're not. Again, this is the mass of object 1 initially. It's not going to change. You don't need an mi1 or m1i. Times the velocity of the object 1 initially.
Couldn't you just use the regular marker on the board? No, because the board's not working.
No, that would stain the board.
On this board here?
Yeah.
No, we're on the board and I want to record, so else it wouldn't work that way.
You can also give us a piece of paper.
Yeah, but it's not the marker, it's the calibration. When you're right here, it senses off. I want to record, so the answer's no. Check. I'm not in the room, we can't discuss this.
Yeah. And can't you just do MV1I?
Yeah, but M1 and M2 are different objects, you need to specify, aren't they? It's like a soccer ball or these two, don't they have different masses? So you need to call one M1 and call one M2. Next, the momentum of the second object, initially, we have the mass of the second object times the velocity of the second object initially. On the right-hand side, we then want the momentum of the first object at the end. So we take the mass of the first object times the velocity of the first object at the end.
I hate these.
Okay, there's a lot of subscripts, I wasn't joking. At the end here, this P2F means the momentum of the second object at the end.
Are we gonna start adding some springs?
So we take the mass of the second object times the velocity of the second object at the end.
Can you write this in a value?
That's a 2F at the end. So here's what's going on. It helps to look. Here's the first object, here's the second object. They are different masses. That's why we're calling them M1 and M2 along the way there. So again, M1, whenever you see M1 in that equation, I'm talking about this object right here. When you see M2, I'm talking about this object over here. They're completely different objects. That's what the masses are.
Okay.
Now, V1I is the velocity of this object initially. So when I'm sliding them together, it's the velocity of this object before they collide. V2I is the velocity of the second object before they collide. So they both have velocities before they collide. That's what those are. They hit, and they might rebound, or they might go off, or they might go off this way, depending on the scenario. So after they hit, they have a new velocity. You think about it logically. Watch, they slide together, they start moving in different directions, so the velocity's got to change. So the V2F and the V1F over here, these are the, so V1F is the velocity of the first object after the collision. V2F is the velocity of the second object after the collision. So in this kind of an equation, what you really want to remember here is that this equal sign is really saying there's a collision going on. This is before the collision. This is after the collision. Jeff, put it in. Now, what we're going to notice for this is we have a lot of variables and a lot of subscripts, so you need to be very meticulous with your work. What does meticulous mean? Careful. Be extremely careful. Okay? Now, to make this a little bit easier, let's look at our first example. Okay? Let's go right into our first example here, if I can actually get to the first example. There we go. A hockey player swings his stick with a mass of 1 kilogram. So, your hockey stick at a hockey club. Now, let's call the mass of the hockey stick, the first object, 1 kilogram. Relax. Let's call the mass of the hockey puck 0.125 kilograms. Okay? Again, first, the mass of the first, so you have a hockey stick and a hockey puck. The hockey stick is going to hit the hockey puck so it travels down the ice. So the stick is the first mass, the hockey puck is the second mass. They are colliding. Okay? So M1 is the mass of the first object, 1 kilogram, right here. M2 is the mass of the hockey puck, which is, if you think about decimals, is 0.125, because you have to convert this. This is 0.125 kilograms. Now, it says he swings the stick with a velocity of 40 meters per second. So imagine you're standing here with your hockey stick. You go to hit the hockey puck. The velocity of the stick before the collision is given as 40 meters per second. So this is V1I. It is the velocity of the first object initially, or before the collision. And after the collision, the stick speed is now 30 meters per second, which makes sense. You collide with something that's going to slow down your velocity. So this here is V1F. This here is V1F. So here's what's going on again. This is the velocity of the stick before the collision, V1I. The velocity of the stick after the collision, V1F. Okay, we've got our masses listed. We're going to have one more piece of info. Fernando, before I introduce that, go ahead.
If a car hits a tree, would you consider the tree a second object?
The issue is this. If the object cannot move, if it's somehow restricted, it's somehow fixed, like a tree, you would have to use impulse theory like we did in class. With FT.
But the tree could bend, so there's a second velocity.
It
Yeah, what
could
if it's
bend,
like
but
a
then-
sign or something?
It could bend, but it could bend and maybe fluctuate, but it's not going to actually move. It needs to actually translate or move somewhere for this to work. Okay?
What about you hit a mailbox, and the mailbox like moves?
Sure, if the mailbox literally comes out of the ground and goes shooting off, then it's a collision with two velocities. Now, the issue there is that this is assuming both objects are free. Look at these two objects right here. They're both free. They're not moved. They're not fixed to the table by any means. They can move. Now, if you have a road sign and you drive your car, or somebody drives a car and hits a road sign, it takes force to get the road sign out of the ground, and then momentum kicks into place. So that's a combined problem where it doesn't involve this. We are looking at two objects that are free to collide with one another and move afterward. Now, the hockey puck is said to be at rest initially. So we could say the velocity of the second object initially is 0. And we want to know what is the velocity after the collision. Again, we're looking at the puck here. If the puck is initially at rest, what is its velocity after? So we want to find the velocity of the second object after the collision.
V2F.
Okay, and that's our question mark.
So would you make us solve for V2F then plug in?
I would solve for V2F algebraically using that last equation we had and then plug all these numbers in. But again, you can start by plugging in the numbers if you'd like to.
Actually, there's one easier way. You can just do 40 equals, because one of the sides you'll have above the number, all the numbers.
One of the sides you will have all the numbers. That's absolutely right.
So it's 40. It's really simple.
Okay. So we've got, relax, gentlemen. We've got mass 1. Leave her alone, Paul. Focus up here. I just see you keep looking over there. Look like you're bothering people in the middle. M1 V1I plus M2 V2I
Keep drawing.
Be careful with your I's and your ones, okay? They get confusing.
You do like the one, you could do like the little
You
line.
can do that, yeah?
Yeah,
That's fine.
what I did.
Is it 80?
Hold on.
That doesn't make any sense.
How much is that?
Actually, it does make sense. The puck will go to 80 velocity.
Now, if you are having trouble with solving algebraically and you want to avoid issues, this is the one time that you probably want to plug in now. Again, if in the past or if you have trouble sometimes solving algebraically, there is a lot of room for error with these subscripts. So if you want to plug in now, it might be more useful at this time. Is that clear? It's one of the few times that I would recommend that maybe you plug in earlier, just so that you can have less of a problem along the way.
I got you.
Okay?
Sheffield, Sheffield.
You know everything at this point. You also know this. This is 0 here. Because V2I was 0, so you can drop that part off. Mass 1 times V1I is going to be 1 times 40 plus 0 equals, again, 1 times 40
That whole
1
thing
times
equals
30.
plus 0 equals, so it's going to be 40, yes. On the right-hand side,
1 times 30 plus.
I got you. I got you.
Plus 1.25.
0.125.
X.
Olivia?
Can we drop the M1s?
No. Oh, yeah, because they're 1s?
Yeah.
No, just like in general.
No.
No?
If you, Olivia, you ready? If they were 2 objects that were identical, then these would all be M, 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 M. They wouldn't have to differentiate if they have the same object. Then you could drop them all. If you have just M in all 4. And we're looking at an example next, actually, where we have 2 soccer balls that are identical. So all the masses are the same. So that's when we can drop them off.
Alright.
Okay?
The answer.
What do you got?
10.6 repeated.
Not right.
Not 10.6 for these.
No.
Luis.
Wow.
80, very good. 80, right? 80, very good. 0.125? You probably use 1.125 or 1.25.
Yeah, 1.10.
Yes.
Oh, 1.125. I did exactly that. And I just,
You're going to have, ready, listen. This is 40. Subtracting 30 gives you 10. And then 10 divided by 0.125 gives you 80.
oh, I divided.
Okay, that's what your equation looks like when you make it look easier. Subtract the 30 to give you 10. And then divide by 125.
Wait, subtract the 30? Oh, yeah, because you can't add it. I see.
What are the units? Velocities.
Meters per second.
Very good, Paul.
Once by land, twice by sea.
Okay, meters per second. Now, here's a question for you. The hockey stick had a velocity of 40 meters per second initially. It went down to 30, which means it gave some of its momentum to the puck. Is that clear so far?
Yeah.
Now, the puck had no initial velocity, and it jumped all the way up to 80. So here's what I'm thinking right away. At first, it might seem like it doesn't make sense, even though we'll explain why. The hockey stick lost 10 in its velocity, 40 to 30, right? But the puck gained 80. A loss of 10 and a gain of 80. How does that make sense? What's the reasoning for this?
Because 10 of it is lost with like in the transfer by just by hitting it.
Okay?
You lose like 10. And
But
then
how could the other one gain 80 if the first one loses 10? First one loses 10 meters per second in velocity,
Because
the other one gains 80.
it's in contact, it loses speed once.
You're making right sense, man, but you're not answering the question. Hold on, let's try. Dan, go ahead.
Because the mass of the hockey stick is 3 times the amount of 0.125.
Exactly right. Exactly right, Dan. The hockey stick is much bigger. So you think about it this way, ready? The object has more mass. So even though it only loses 10 meters per second, it's going to cause much more than 10 meters per second difference in the other one, because the other one is so minuscule. It's like if you took, imagine if you took a baseball. I I don't know ladies, I don't know how to be sexist, but I know the guys who have probably done this, because I've done it. Ever hit a golf ball with a baseball bat?
Oh,
Yeah.
What happens?
I do it in my free time.
Have you
What
ever?
happens? Seriously, have you ever done it really?
Get out of here.
Have you
It
ever?
gets launched, doesn't it?
Yeah.
I mean, it really does.
You can barely see it.
If you hit a baseball with a baseball bat, though, it doesn't go nearly as far, because the mass is much larger.
That's very mean.
You're Tyson short.
What if
Now-
you did baseball with a golf club?
It doesn't go as far as it would go then with a golf ball. It goes to the mass. Okay. Yes, exactly, guys.
Have you ever hit an apple with a baseball bat?
I'm sure it was explosive.
It did.
My golf
Can't
ball.
just leave it out.
My golf ball.
Yeah, my-
Just
This kid I know hit a basketball with a golf club and it snapped and like the.
It's not a golf ball?
I got a great example.
Well, that makes sense, because there's so much pressure.
I hit a big.
I left my friend.
There's so much pressure inside the basketball that it like acts as like a responsive force, and it's not gonna break your basketball like that. The yield strength scope of the shaft of the golf club was lower than the yield strength of the basketball, which causes that scale.
Once I had a tennis ball. There's this example where you put a tennis ball until a basketball and you drop it at the same time, and the tennis ball shoots up. Is that because of this?
It's also transfer of energy there, yeah, but it is this.
This
I did that last year in my class.
Yeah, it's so cool.
Yeah,
Once you start
You
doing it,
literally
you
just
can't
put hold
stop.
together and drop it and launch it.
Yeah, I just do it from
I'll try to bring one to next time.
I
I didn't do it this year, I should do that.
can get Mr. Eddie. Let us-
I know, I got a ball. I've got a bunch of tennis balls, who's the best?
Why do you play tennis ball?
Okay. Just from having for physics,
Oh.
for they're useful for other experiments and stuff. All right, let's take a look at this one now. One soccer ball is kicked down the field and collides with another soccer ball that is at rest.
Oh, I've done that before, but just with
Okay.
my.
Now, assume the soccer balls are identical. Okay, assume that they're identical. If the ball that is moving before the collision has a velocity of 12 meters per second east before it hits the other ball, and a velocity of 4 meters per second afterward, then what is the velocity of the ball that was initially at rest after the collision? Now, the first thing to notice in this kind of a problem is this key thing right here. Assume the soccer balls are identical, which means that if you want to call the first object M1 and the second object M2, that's fine, but they're the same. So call both objects just M. Again, in our equation usually looks like this. You don't have to write this down because we're not going to really use it here.
So you can cancel out all the masses.
Normally that's our equation, but since the masses are all identical, just call them all M.
Do we even need to call it M?
I'm going to show that they can cancel first, but if you know that, no, definitely not. Not that if you're smart, it's if you've done it already. Alright, so, when we do that, it makes this a lot easier. Okay, all the masses cancel. Stop with the sounds back there, guys. I'm seriously close to giving somebody jugging here. It's sad. I don't like to, but it's getting annoying. Not in this class, no. Now, we have M in every single spot, so we can cancel all of them. They all drop off. And that leaves us with a very, very simple equation. V1I plus V2I equals V1F plus V2F. You don't need to ever memorize this, simply because it's very easy to derive. If the masses are the same, call them all M and drop them all off. And remember, if you ever have a variable that's in every single term, you can always drop off. That's why those masses all cancel. Now, what we're going to see here what we're going to notice is that this problem is simply dependent on our velocities, which makes sense because the objects are the same size. If these two objects over here had been the same size, all that matters is their velocity. It's just like the example, if you have, imagine, ever see in football practice, football players do the drills where they have to run head on each other, see which one can have more force in a sense?
Yeah.
If there were
so
two,
much
if there were two players with the exact exact same mass, in the end of the day, it's which one would go faster, really. That's what matters.
Either.
Because if they had the exact same mass, and imagine if they had the exact same velocity, they would hit and actually just stop. That's what happened. Same mass, same velocity, they hit together and stop. But if one has more velocity, it pushes the other one over.
And what about like Newton's cradle? How would that work? Because over here they have the same mass, but the other one is
It's a complete transfer momentum. It's because
how
one is at rest, the other one is in motion. This has a motion of, say, 3 meters per second. It hits, it stops, because the other one was initially rest, and it transfers the momentum there.
Yeah, like
Then it goes back.
over here, it also has, zero initial velocity.
Mhm.
So why would the first one keep moving?
Say again.
Why would the first one have to be at when the first one stops?
Okay, Newton's cradle is what's called a completely inelastic collision. So there's a perfect transfer of energy and momentum. Whereas with like things like soccer balls, there's things like friction in the ground that are going to cause that to be different. Now Newton's cradle, you know, is not perfect
I
either.
know, but then wouldn't you have to have a constant for the necessity?
Yeah, but Stash, the problem is not asking what's happening to the object afterward. It's, you're told that it starts with 12 and it ends with 4. So part of its momentum is transferred into a not completely perfect zone. Newton's cradle is an approximation of a completely perfect transfer of that momentum. Whereas here we're looking and saying, well, this just slows down. That's all it's doing.
There'd be like a big difference between, like, say, like a rubber ball and a metal ball. So like, how is this equation?
This is an equation of momentum. If you were doing this and you were an engineer and you were actually looking at collision of two objects, you have kinetic energy that's involved, you have momentum, you have to start looking at like, you know what, there might be heat between the two objects involved. So there's a lot more going on. That's what causes this to not be perfect when you're doing this. Now, in a real, like in a perfect world with Newton's cradle, exactly. It would be like 12, hit 0, 12, hit 0, 12, hit 0, and it would do exactly that. Yep. But this is an example where it's not like, we're not looking at Newton's cradle, we're not looking at a perfect equation or a perfect transfer of momentum. Right?
Wait, one thing I've always wondered, why does it make a difference whether there's, you know how the balls that come down and hit each other?
Why is it just one in between?
Yeah, why, the amount of balls that are in between, why?
You can't laugh because you asked the question.
Why does that matter?
Why won't it
Why
matter?
does it make such a difference if there's one ball compared to like 4?
I mean, okay, first of all, this is going into vibration stuff now. One object hits the last one, it sends like a pulse, and there's a mini like vibration that's sent through the other ones. Now, it comes out to the other one and causes it to rise up. If you drop 2 of them, there's double the momentum, so 2 of them are going to shoot off. And that's what's transferred back and forth. The number of metallic spheres in between there is
Circular device.
is not necessarily going to impact it. It's not necessarily going to impact it as far as transfer goes. Now, if you wanted to drop 3 of them, and you had 3 on this side, you would need a total of 7 to at least have 1 in between. Follow what I'm saying?
So the numbers actually
Yeah, that's why it's always odd. You always notice the number of the spheres in Newton's cradle is odd every time. Check it out. Yeah, there's 5. So you can either drop 1 and it'll knock 1 up. You can drop 2 or knock 2 up. If you drop all 3, try that sometime. That's an interesting one. Try dropping all 3 and see what happens. Okay?
I think we did that.
All right. We know the ball that's moving before the collision has a velocity of 12 east.
It's 3 meters per second. Why is it so expensive?
Next, the velocity.
Because it's so cold.
The velocity here of the second object, it's initially at rest. So what do we do to that? It's initially at rest. Next, the velocity of the first object after it collides
4x.
is now only 4 east. I'm putting east for a reason.
Does this mean negative?
And we want to find V2F.
East side.
It's actually
So,
not gonna be negative.
East side, east.
When we have an object moving east, it's like this. This object is traveling east like that. Now, what happens is it's moving at 12 meters per second. It hits into this object. It slows it down and causes this object to shoot off. So they're all still moving east. So our answer in this problem should still be positive. In some examples, though, we're going to see when two objects collide, they might rebound off each other. So this would have like a positive velocity. This would be considered a negative velocity. And when they rebound, this would now be negative and this would now be positive. So the east and west is very important in these problems because it tells us if there's a positive or negative velocity, meaning which way is it going to move after the collision. So again, these objects, they might collide and just spring off each other. Or they might collide, believe it or not, and both go in one direction. And that can easily happen. We saw it before. By sliding through each other, see how they both continue to move this way after they collided? Because the momentum of this one was so much greater than the momentum of this one. Okay? So for this kind of a problem here, since they're both east, we can consider both of them positives. Subtract the 4 from both sides. We're going to get the velocity of the second soccer ball is simply 8 meters per second. Okay? Now, notice here, the first object was the exact same size as the second object. How much velocity did the first object lose? How much did it lose from 12 to 4? 8. What did the second object gain? It's a perfect transfer in that sense, simply because they have the same mass. In the last example, think back. The one object lost 10 meters per second, the hockey stick. The hockey puck gained 80 meters per second. They were different numbers because the masses were different. But when the masses are the same, like this example here, the amount of velocity the first object loses is equal to the amount of velocity the second object gains, which is exactly how Newton's cradle worked. Newton's cradle, the first object has some velocity. It hits, it loses all that velocity, and it sends it all to the other object. That's what's happening here. Now this object happens to still be moving with 4 meters per second afterwards, so it doesn't stop like Newton's cradle does. Okay? But here, we have the example where it loses simply 8. It's a net loss of 8 meters per second, so the other one has a net gain of 8 meters per second. Okay? Before I go on, you don't have to say a word, just show of hands. How many people, just show your hands, are familiar with what Newton's cradle is?
Oh, I'm bleeding. No, no.
What do you mean with next step was like what it is?
I went a little too high.
If you start bleeding, you don't
Back.
Now, let me go over what it is real quick to give you a quick scenario.
But like, you put your hand down. Like balls, back long.
Yeah. It's like balls.
Newton's cradle. Okay, here's Newton's cradle. Guys, stop. Whatever you're doing, stop.
I'm just watching it.
Take a look at the top diagram here. Okay, you have one mass that's being raised up and dropped. Put it back in the container over here. Okay, over here.
Troublemaker.
One object is being raised up, is then dropped. We see it collides and it transfers momentum. So I think the question was about, does it matter how many objects are in between the ones that are in motion? And we're going to see how there's 3 in between. But if you were to drop, in this case, you see how there's 2 of them being dropped, and 2 of them rise up. 2 are dropped, 2 are... The thing is that it's odd for that reason.
Would the middle one go both ways? If you chop all
If you take all 3 and drop it,
would the middle
when it hits, the middle will probably go with these ones, and then it'll go with this one. Yes, exactly. It will attach itself to whichever one is in motion.
I watch it.
Exactly right. So if you have one of these at home, check it out, take a look. This is what the transfer momentum is really looking at. Okay? All right, let's look at the last example here, or one of the last examples for today. Please write it down.
5 minutes.
It's hard to write it down. Guys, one day you're all going to be in the circus, because you're all acting like a bunch of clowns. Stop doing that, please. A person with a with a velocity of 5 meters per second west. If he lands on a cart with a mass of 20 kilograms, with wheels on the bottom that's initially at rest, what will their combined velocity be immediately after landing? Write it, and I'm going to give you a quick demo of what it looks like without getting hurt, hopefully.
You want me to need a second diver?
You want me to catch you?
Look at what wheels on here. There's no.
I can catch you.
All right, so here's what's
I
happening.
can be your wheels.
No, so, this object is on a cliff.
Bro.
This object is on the ground level. This object launches itself off the cliff. It lands. Imagine, so think about this. This is, you see this in movies all the time. It's like a stunt double jump off an object, land on like, say something with wheels on the bottom, and he starts moving on it, right? So this object jumps off, lands on this object. Because he has velocity, it causes them both to start sliding forward together. Okay, so again, before is right here. This object jumps. Here's before, collision, after. So beforehand, the masses are separate. You see this?
Yeah.
But when afterward, what happens to the masses?
No, they're not.
They combine.
They combine. They're not the same, but they combine masses. So here, before the problem, we're going to have M1 V1F, M2 V2F. Let me start over. Before the collision, M1 V1I, M2 V2I beforehand. But afterward, the objects have now collided and they're stuck together. So they start to slide together afterward. So now their masses are lumped together. So let me show you what I mean. Beforehand, we have M1 V1I plus M2 V2I. Remember, the first object is moving beforehand. The second object is stationary. It's a crate. So this one is not moving. So we don't have to worry about it for now. Afterward, though, they are lumped together. So here's what you write afterward. You put their masses together and simply multiply by VF. Again, if two objects are together and they are sliding forward, they must have the same velocity. Look at this. Ready? Watch. I slide this. The velocity of the one object is the same as the other. So I do not need to specify my VF. I can simply say that they have a velocity and they are together afterward. We don't have to write this as two separate parts.
What about inertia?
About what? Inertia? What about it?
Let's say that the person jumps on top of the car. So it's going, the person's going at the same speed, but what if it starts to like, doesn't the person not go exactly the same speed?
I mean, if you're in a car and the car's moving at 60 miles an hour, you're moving at 60 miles an hour. I mean, this, realistically,
like if
sure
you're on
there's air
a train?
resistance and this and that and all that stuff, but
Oh, is that like if you're like, say you're on like a train that's going like 60 miles an hour and you're playing pool, and you like hit the pool ball,
the ball's
like
going
it's
60
gonna move normally. Yeah.
plus whatever you have.
I play pool all the time on trains. All right, on the subway.
Now, we know the mass of the first object is 50. Let's fill in, please. And I rarely fill in. I'm doing this to make it easier on this thing. Now look at the velocity, 5 meters per second west.
It's negative.
Thank you.
Good shot, Joe.
That's how I roll.
That's how I roll. Okay? This problem is actually easier mathematically speaking.
This is a plus sign between 50 and 85.
No, these are multiplying each other.
Might actually
They're just multiplying each other.
Wait, I got like negative 3.5.
You should get a negative answer, I hope. Think about it, ready? The person jumps off the cliff west, lands on the cart, so together they're going to continue to move west. So your answer needs to be negative. Okay? Your answer needs to be negative. You're going to get an answer of negative 3.6. And why is there only one answer for afterward? Because the objects are now together. The objects are now together. Tonight, practice, page 219, number 2. Okay, there's another one, but I'm going to wait till we have to do a few more problems today.
Test that. We should get one more out of test.
Nothing serious.
That's
double period, guys.